let me welcome you to the 30th lecture of Drilling and Blasting Technology course. In this lecture, we will continue to the techniques of surface blasting, which we are continuing from the last two classes also. And as you know that in this class, let us first retrospect what we did in the previous lectures. In the previous lectures, we are observing the influence of the different designing parameters. We have covered hole diameter, hole length, inclination of the hole, stemming length, subdrilling length, bench height, etc. In this class, we will discuss the influences of other parameters like burden, etc. also, and we will mostly cover how the designing can be done. So, let us see our learning objective. Our learning objective remains same as from the last two classes also, to understand the different factors influencing surface blasting, to design a surface blast, to analyze the results of the surface blast. So, like every class, let us look into a video which is available in the YouTube also. This is the blasting done at a copper mine pit. So, you can see the blasting is being carried out here, you are able to observe, and you can see the brownish fume has come out. In the next blast also you can see, say you can see little bit brown flame has come out, but other places the whitish flame has come out. So, while we are discussing our explosive properties, that time we are unable to cover all the properties because of the time constraint, but most of the properties we have covered, and probably this property is not covered here there, that is the fume characteristics. Though this property has been extensively discussed in the textbooks like written by Dr. Pradhan, etc., SME handbook also, in the different internet literature also it is discussed. The fume characteristics is basically gives us the idea about the how the explosive is manufactured and whether it is operating properly or not. So, here also you can see some of the brown flame has fume has come out. So, basically this is a phenomena where an important property that is called oxygen balance has come out. If you see the major ingredient of the explosive is the ammonium nitrate. Okay. We mix ammonium nitrate with the fuel oil, mostly it is diesel, and ammonium nitrate act as the oxidizer, and that is the main source of the nitrogen, and fuel oil which is basically CH, carbon and hydrogen, that is basically the energy source. So, on reaction it converts into the flame of different types, and it is converted into the fumes of different types, and these gases are CO2, H2O and different nitrogen oxygen gases. So, it may be N2O, it may be NO, it may be NO2, like that. So, different nitrogenous gases are come out apart from CO2 and H2O. So, what will happen if the nitrogen source is becoming more than the oxygen source, then the N2O will come out more. If the carbon source is becoming more, then the most of the oxygen will be taken by the carbon and hydrogen, and that is why the oxygen for the nitrogen become limited. So, that is why what will happen, N2O will come out in that case, and N2O is basically representing this brownish flame. So, fume characteristics is very important, and that must be considered when you are observing the blast fumes. You have to analyze your property of the explosive, you have to reconsider about the manufacturing of the explosive properly. So, oxygen balance is very important, and with best oxygen balance only the proper energy can be utilized. Now, let us look into the designing of a surface blast. Surface blast design, our first property is the burden, which is very important. So, basically we have already discussed while we are discussing how to select the burden, that is the optimum burden. It may be inadequate burden, it may be more excessive burden. Those are already discussed, and how the burden can be selected, how the burden can be what should be the importance of the burden, that is already discussed in the explosive rock interaction. So, in general what will happen, we are having some rule of thumb which in general we try to follow while we are practicing our blasting. Generally one criteria we will discuss here, say it may be one criteria where we can start with the bench height, and as a rule of thumb where we are trying to design a blast, we will select our blast hole dia as a function of the height. So, in this first concept we start with the bench height or the face height. So, let me before going into the detail, let me clear you first thing. Always a blast design has to be finalized from the trial blast experiment. That means, trial blasting 1, 2, 3, 4 has to be carried out, and every time we will modify different parameters in this trial blasting to finally arrive at the final blast design. But we have to start trial blast with some design, and all these guidelines which are given, this is say based on face height. Another time we will discuss about the blast hole based on the blast hole dia. So, all these guidelines which are given, or n number of guidelines are available in different textbooks, are valid or to be utilized for starting in the trial blasting. The trial blast 1 has to be carried out. The trial blast 1 must be closely monitored, and observing the result of the trial blast 1, the trial blast 2 will be designed. Then the observing the result of trial blast 2, trial blast 3 has to be designed, and like that way the trial blasts will be designed to arrive at the final blast design, which basically satisfying us about the performance of the blast, or we will see whether the desired blast result in terms of fragmentation, in terms of throw, in terms of Mach profile, in terms of blast vibration, etc., we are achieving or not. So, final blast design must satisfy those results, then only we will adopt that final blast design. Otherwise, we will go for the trial blast, more number of trial blasts. So, in this first guideline, we are considering the base is the bench height. We have to design our blast from the bench height, and the diameter is a function of bench height 0.1% to 2%. The burden is a function of diameter, which may vary 25 to 40 times of the diameter of the blast hole, and obviously this depends on the type of rock. Spacing is a function of burden, which may vary from 1 to 1.8 times of the burden. Inclination of the hole angle may vary up to 30 degree. Normally, we do not go for inclined hole angle unless and until it is essentially required. Sub drilling is required in few cases where it should be 8 to 12 times of the diameter of the blast hole, or it may be 10 plus 20% of the bench height, or it may be b by 3 in different conditions, and charge length must be greater than the 20 times of the diameter. You know, if the charge length is less than 6, then it becomes spherical charge. So, to avoid the spherical charge and to achieve a column charge, it must be more than the 20 times of the dia. The stemming can be calculated using this formula, where Z is the fly rock factor, 1 for normal blast, 1.5 for controlled blast. A is a rock factor, this is the rock factor given. So, this is basically developed by Konya et al. This is the explosive mass for 8D length of explosive column, and this is the relative weight strength of the explosive considering ammonium nitrate fuel, strength of ammonium nitrate fuel oil as the base, that is 100. So, using this formula, the stemming length can be determined, and obviously it is considered the stemming length is this one and the total other length of the hole is filled with the explosive. So, this is the prime consideration of this one. You can see the rock factor is becoming very high for the hard rock and less for the soft rock. So, it is expected that the stemming must be more for the soft rock and must be less for the hard rock. So, the quantity of charge must be more in case of hard rock. Deck charging may be carried out, and it must be greater than the 6 times of the diameter, so that sympathetic detonation can be avoided. That means, if this is the whole section of the hole, this is the first charge which is being blasted, then some deck material is provided, then the second charge is provided, and finally, the stemming is provided. So, this decking length must be greater than 6 d, this inert material which is creating this deck, this decking length must be 60, so that the shock generated by the explosive at this position should not sympathetically initiate this explosive. So, to avoid this sympathetic detonation, the deck charging length must be greater than the 6 d of the diameter, 6 times of the diameter of the hole. It is expected that the initiation from this, for this one, must be tapped from this to this place either by a detonating fuse, or it may be initiated from the top if we are very sure about the non scattering of the delay. Otherwise, it is expected the initiation must be tapped from this position to this position using a detonating fuse or something like that. The charge density is calculated. Say this is the linear charge density, obviously pi by 4 into d when it is expressed in millimeter, d by 1000 square. So, this is basically pi by 4 r square, and delta is basically nothing but the density of the explosive. Okay. So, this is the formula. If we are using a cartridge charge, as the d is the whole dia, if we are using the cartridge charge, then R d is basically the factor, that is the decoupling ratio. R d is basically the decoupling ratio, which is nothing but the ratio of the cartridge dia and the whole dia. So, suppose if we are using a cartridge, if we are using a cartridge explosive like this. So, this is the diameter of the So, this is the diameter of the cartridge. This is the hole dia. So, basically d by d is the decoupling ratio, which is considered here as the charge density. So, for cartridge explosive, this is the linear charge density, this is for the bulk explosive, this is the linear charge density. So, this is more or less Coney's theory, which we have discussed, basically carried out based on the bench height. Now, let us look into another one, which is basically the theory of Langefors and Kihlstrom. So, Langefors Kihlstrom has given this criteria where we start our designing of the blast from the diameter of the hole. So, the person or the designer first has to choose the diameter of the hole, then the rest of the parameter can be easily calculated from the blast hole diameter. But Langefors Kihlstrom has given a guideline for the selection of the blast hole diameter. Their guideline is basically depending on the production rate and depending on the strength of the rock. Suppose the excavation procedure is aiming a production rate which is expressed in meter cube, this is bank meter cube, that means in situ rock material per hour. If that production is expected, say the mine is expecting that per hour 500 meter cube of material has to be blasted. So, that 500 meter cube material will be blasted if it is medium to soft rock, then it is coming here. It may be hard rock, then it is actually this is for small dia, it will go to the large dia 1. So, that is why the diameter basically will depend on this production factor and it will depend on the strength of the rock also. So, he has classified strength in basically two part, one is hard and another is soft, medium soft, that is greater than or less than 120 megapascal, and based on that he has given the guideline of the different production rates and the diameter of the drill correspond to that production rate and that strength. So, basically these guidelines will give the idea of the user about that what should be the possible diameter of the blast hole. He has also categorized the blast hole in two broad categories. One is the small diameter hole. Small diameter hole which is less than 165 millimeter dia, he has considered that is as a small diameter hole. So, this 150 comes under small diameter. If you go through his original literature, his books, textbook, you can easily find out for the large diameter also what he has discussed. In this class I am not discussing the large diameter, because it is basically the guideline, actual guideline you can have there. So, this small diameter is for 165 less than 165 mm dia and large diameter is considered if the diameter is more than 165 mm dia. So, in that case he has classified it like this way, and obviously this table will become different for the large dia. This table is for small dia which is presented here. So, the basis of Langefors Kihlstrom is the selection of the hole dia first, then the other parameters, other blast design parameters will be calculated based on the hole diameter. The guideline for selection of the hole diameter is given in terms of the production requirement or production target of that excavation area or the mining area and the strength of the rock on which the blasting has to be carried out. So, basically based on that he has given the idea about the whole dia. The next purpose is the bench height. Basically bench height is a function of loading machine also. So, the loading machine requirement is very important. So, he has given a guideline that if a person is using a bench height of 8 to 10 meter, then he may opt for blast hole diameter of 65 to 90 millimeter, and it is expected a front end loader can give you better loading equipment. However, in case of a little bit larger bench height, we have to select a little bit larger blast hole dia, then the shovels may be a good equipment for the loading machine. However, this is the practical easiness of the handling of the material. If the material is very strong, very abrasive, and in those cases high specific gravity front end loader may not give the sufficient digging force, because the digging force of the front end loader is very limited. In those cases this front end loader may be replaced by a hydraulic shovel or maybe a rope shovel also in this place. So, basically the loading equipment depends on the how much digging force is required at this position. However, this part is not a basically blast design part, this is for required for our own understanding only. So, for a small diameter hole, what should be the different blast design parameters? That will be, as he has already told, that it is must be based on the diameter of the blast hole. So, you can see the burden, spacing, stemming and subdrilling as a function of diameter of hole, diameter of blast hole for different compressive strength of the rock expressed in megapascal, and that is categorized as the low strength rock, medium strength rock, high strength rock, very high strength rock. And you can see for low strength rock burden comes around 39 D, and in medium the burden value is decreasing, high further decreasing, very high again decreasing. So, basically burden value is decreasing with the strength of the rock, stemming value is decreasing with the strength of the rock 51, 47, 43, 38 D. Stemming value is also decreasing, but not that much significantly 35, 34, 32, 30. Subdrilling length is basically increasing with the increase in the strength of the rock 10, 11, 12, 12. So, we need more subdrilling if the rock strength is high. We have to design for a lesser burden, lesser spacing, lesser stemming if the rock strength is increasing. So, that is why this is as per our requirement, because the explosive charge quantity required more for the stronger rock, and that is why this lesser in the burden, spacing and stemming basically ensure us the charge per unit volume of rock will be more if the rock strength is high. So, basically this is the general consideration, but the guideline is given by the Lange-Fors-Kihlstrom for this. Again let me remind you that this guideline must be followed for designing the trial blast. Based on your result achieved from the trial blast, you have to modify your design. Say you may start with a 39 D burden for a this type of condition, then you may increase up to 40 D, you can see the result. You may decrease it to 38 D, you can observe the result, and based on that modification you have to see the other parameters. You have to change the other parameters also, like that way n number of iteration may be carried out to finally achieve to a final blast design for that particular mine. In fact, I am not discussing the guideline which is given by the Lange-Fors-Kirchhoff for the large dia holes, because obviously 165 mm is not the end of the drilling diameter. Presently, we are using 350 mm diameter drill hole also. So, that is why large diameter holes are also there, that is also used for different blastings. That guideline is also given by Lange-Fors-Kirchhoff in its book, but because of the time constraint we are not using the we are not showing it in this lecture, but I strongly suggest you must go through all those guidelines in your further study. But one thing I must discuss, that the burden value, say the heart of the blast design is to establish the burden value, and if you go through the literature you will find out not only the Koniye and Lange-Fors-Kirchhoff, n number of burden value formula are there. Say this is the Bhutuguri formula, where burden is 24 d, d is the hole diameter plus 0.85, Hagan's formula 25 to 30 d, Ash formula delta B d, where delta B is the burden ratio varying from 14 to 49, Anderson formula is this one. And in fact, once I have searched literature for that, and I have found that there are 16 burden formula are there, 16 formula only available only for burden with different influencing input parameters. And if you try to use all those 16 formula for calculating burden in your own case, you will find out the range of result you are achieving using this formula, this formula, this formula, this formula, like that 16 formula is significantly very high, maybe 5 to 10 times of the burden value normally which you are expecting. So, that is why this basically creating a parallax about the burden value, and that creates the problem to the user. So, it is always suggested one must go through the original literature where these values are given, and as these are mostly the empirical relationship, empirical formula established based on some case studies. So, that is why their applicability range is lying within the limit of those case study. So, that applicability range of those formula is very important prior to utilize those formula as your design criteria. So, that is why the user must be very careful about the burden formula which he would like to use for his own case. Now, we have already established the burden spacing etc. So, this is the burden spacing, hole depth, then the stemming, subdrilling, all are established, and now these are charged and we have to blast this one. So, while we are going for blasting the multi row or multiple holes, it is essentially required that we have to provide some delay in those holes. So, based on that we have already discussed that our holes our design can be considered in different categories. The first one is row to row, where a row of hole will be blasted simultaneously, and we have to provide delay between two consecutive rows, so that prior to blasting of the second row, the first row will be blasted and a new free face area will be created at this position. So, this is the essential requirement, and we have to provide a delay between these two rows. How we will assign the delay in these two rows of holes? We have to understand the burden movement speed for these, and normally through our high speed photography system, it is more or less established the burden movement speed varies between 3 to 5 millisecond per meter, and that is why if you are using a 4 meter of burden, you can consider the 20 to 25 millisecond delay may be sufficient for assigning first row to the second row. This is essentially required for another purpose. This delay should not be very high, so that the first row will be dispersed and the second row is not moved at all. It is essentially wished the first row, the rock pertaining to the blasted pertaining to the first row must be at air, not in the ground, prior to at the time of blasting of the second row. So, that will act as a curtain to the second row of curtain to the rock, which are being fractured by the second row of holes. So, basically this is the guideline more or less has to be followed for row to row blasting. If we are willing to do it for the V cut, the procedure will remain same, that we have to blast this hole, ahead of blasting this one, so that a new free face area will be created like this way, and then the effective burden of this hole will become this one, and when it will be blasted, this portion of rock will throw in this direction and they will collide to each other, and the better fragmentation will be observed. So, this is for the V cut blasting. Again we will try to provide the delay between two consecutive rows of blasting in the V cut also, considering the burden movement speed. The same thing is there for the extended V cut also. So, that is more or less we use for the assigning the delay to the surface blasting. Here one very important parameter is the scattering of the blast, scattering of the delay in the blasting, and you can see because of the scattering, that means the fluctuation of the achieving the actual delay value in the practical field, there may be possible that the simultaneous blasting may occur in this delay. So, green is delay number 2 and violet is delay number 3. So, this overlapping of delays occurs here, and it may be possible that this delay is blasted after the blasting of this delay. So, that must be avoided. So, we have to select a delay time and we have to select a delay detonator which has a very less scattering, and that is why nowadays electronic detonator is becoming very popular in the surface blasting. So, that is why this is very important in the surface blasting, and one must follow the proper sequence and must avoid the overlapping of delays in its consecutive holes blasting. The another important is the sequence of delay in the down the hole situation and in the surface delay. Generally what is happened, if we are using a nonel or that type of material, we provide the detonator inside the explosive, and the nonel is being initiated by another detonator or maybe another nonel also. And in a multi-row blasting, multi-hole blasting, if the total delay time is very high, say maybe 500 millisecond or 1000 millisecond, 2000 millisecond, generally more than 1000 millisecond we try to avoid, but if it exceeds for a very large blast, then the fly rocks coming out from this portion of the rock blasted by the first hole may come drop on the surface connection and cut the surface connection. So, it is always wished that before blasting of the hole, the surface connection must be blasted properly. So, a significant delay should be provided to the down the hole delay, so that the surface connection will be over prior to the blasting of the rock. So, that is why down the hole delay is very important, and it should be long enough so that surface continuity will be over before the down the hole delay, blasting of the down the hole delay, and the sequence of blasting will basically be dictated by the delay provided in the surface. So, while we are having these two rows of holes, the delay provided in the surface between this row will remain same as we are using the down the hole delay of same amount in all the holes. So, basically the surface delay will remain the delay of the actual time of blasting, and surface delay should be used small depending on the burden movement. Sequence should be follow the pattern in surface. Down the hole delay must be same and it must be long enough, so that the complete blasting will be over before the first hole has to be blasted. One must be aware, I am again dictating this one because it is already discussed once in the explosive rock interaction. Burden must be optimum, and optimum burden will give us the best result. If the burden is excessive, then the rock will not move and gas energy will be released in the upward direction. So, you can see a similar type of situation where the fragmented rock will be thrown in the upward direction only in this part, unbroken rock will remain at this part. And if we are having a inadequate burden, small burden, if we are having a inadequate burden or small burden, then the fly rock may be generated at this position, noise will be generated at this position, and this type of big boulder may struck onto the houses at a larger distance. So, basically inadequate burden no, excessive burden no, we need only optimum burden. So, optimum burden is very important in the blasting, and the design basically lies on the selection of the optimum burden. So, let us stop, you can have more reading from these books. Let us stop at this position. I strongly recommend you the reading of this book and these two basic books for having a more details about the blast designs, especially surface blast designs, also SME handbook and blasters manuals of IACE is also available, and also of different manufacturers blaster manuals are also available, that may be also very useful for the further study. So, let me stop at this position here. Next class we will continue with the blast designing for the underground mine. Okay, thank you.